Hello, my name is Uche Daniel and I'm presenting OmniSearch. OmniSearch is a production-grade multimodal product search system I built from scratch. This project demonstrates my expertise in deep learning, multimedia AI, vector databases, and full-stack engineering. The core problem I'm solving is how can we enable users to search for products using text, images, or both, and deliver personalized results that understands context. Traditional keyword search fails when users can't describe what they want in words. With OmniSearch, you can upload a photo of a dress and search for formal occasions. The system understands both the visual style and the semantic index. So I'll be showing you the architecture. So let me walk you through the architecture. So as you can see on my screen, the first architecture is the embedding layer. I use OpenAI Clip Model, which is a visual transformer that maps both text and images into a shared 512 dimensional vector space. This is the magic that enables cross-modal search. Then secondly, the vector database layer. Embeddings are ranked, are indexed, and weave it using HNSWA, a hierarchical navigable small word graph that enables sub-millisecond similarity search across millions of vectors. Then thirdly, the ranking layer. Raw similarity scores aren't enough, so I implemented a custom re-ranking algorithm that combines vector similarity with metadata matching weighing color, category, and text similarity to deliver results that feels intuitive. Then the last layer, which is the agentic AI layer. A personal shopper agent uses RAG, retrieval augmented generation, to combine search results with user purchase history, then uses an LLM to generate personalized recommendations with explanations. So this is the flow of how everything goes. So the clients puts in their request either as a text, image, or text and an image, and then it goes to the fast API endpoint, and then it goes to the clip embedding services, which converts the text to 512 dimensional vector spaces, or the image to 512 dimensional spaces, then fused embedding, then goes to the Vivid vector database, and then goes to the ranking model. So the ranking model is what the formula here is what we use to rank each of the search results. Then goes to the API response, which then gives you the top 10 rank results with score. So the next one is the deep learning and multimodal AI. The foundation of OmniSearch is CLIP, which is contrastive language image pre-training by OpenAI. I'm using the VIT-B32 variant, which is a visual transformer with 32 by 32 batch processing. What makes CLIP powerful is contrastive learning. It was trained on 400 million image text pairs from the internet, learning to align images with their description in a shared embedding space. Let me show you how this works in pattern. When I embed the text, let's say red running shoes and an image of red sneakers, they produce similar 512 dimensional vectors. The concise similarity between them measures semantic alignment, not prism matching. For multimodal search, I implemented fusion embeddings. That's it here. Embedded feature embeddings. When user provides both text and image, I compute a weighted combination. The default is 60% image, weight 40%. The default is 60% image weight, then 40% text weight, but this is configurable. This allows user to say, find dress similar to this photo, or for formal occasions, combining visual similarity with semantic intent. So the second one is the vector database indexing. So for vector storage and retrieval, I chose Weavit, an open source vector database with native HNSW indexing. HNSW, hierarchical navigable small word, is a graph-based algorithm that achieves logarithmic search complexity. Instead of comparing against every vector, it navigates it navigates through a multi-layer proximity graph, dramatically reducing search time. So I implemented IVF indexing. So what it does is, as an alternative, so IVF partitions vectors into clusters and only searches relevant partitions. This is a trade-off. HNSW is faster for most queries, but IVF can be more accurate for high dimensional spaces. So in my implementation, I use two-stage retrieval. So the first one is the two-stage retrieval. So the first is wave it, which returns the top 30 candidates using vector similarities. Then my constant ranking models, which will ranks them to return the top 10 most relevant results. So the next part is the RAG personal shopper agent. So one of the most sophisticated features is the personal shopper agent, an agentic AI system that uses RAG to deliver truly personalized recommendations. RAG stands for Retrieval Augmented Generation. Instead of asking an LLM to generate recommendations from its training data, we first retrieve relevant context, the user's purchase history, their color, their color preference, their price range, and the top search results. Then we augment the LLM results with this grounded context. So you can see it on the screen here. So the recommendations are grounded in real data. The LLM can only recommend product that exists in the catalog with explanations that reference actual users' history. So this architecture ensures recommendations are grounded in real data. So that is that with that. So the tech stack that was used in creating this project was Fast API, which is the backend, Next.js system, PyTorch, Weaveit, MongoDB, Clip, Feature Transformer, Docker, AWS SageMaker, and React 19. Although the AWS SageMaker was not fully implemented, but it still works. So the entire system can be deployed in a single command using Docker Compose Up. So yeah, and then A/B testing framework. So in the production ML systems, shipping a model isn't enough. You need to measure the impact. So I built a complete A/B testing framework directly into the API. The system supports multivariant experiment. For example, comparing baseline vector search against enhanced ranking algorithms. Users are consistently assigned to variants using deterministic hashing for their user ID, ensuring that they always get the same experience. Every search, click, and impression is logged with variant metadata, enabling calculation of click-through rate, dwell time, and conversion metrics per variant. I also implemented a statistical significance testing to determine when we have enough data to declare a winner. So this is to demonstrate my understanding of production MLOps, not just building models, but building systems to continuously improve them. So I'll be walking through a live demo of how OmniSearch works. So when you put black running shoes, let me type it text black running shoes and click on search. So it's you can see it brings the black running shoes first because it understands the context, and the other search results that accompany it are results that are similar or close to the search. So when the user inputs a text, it goes like that, and it brings out the top 10 search results like we explained in the architecture. So then let me impute an image. So you can impute both an image and a text. So let me impute an image. Okay. Okay, so So I downloaded this from the internet. So this is the image of a running shoe. So we want to just query it without a text. So you can see here it shows image search, and you click on it. So it's going to search. It's going to be using the picture of the shoe to generate results. So like I said earlier, from the user prompt, it goes to the fast API endpoint, and then goes to the clip model. So, and then goes to the ranking model, which helps to get the 10 results that match what we are searching for, and then goes to the comes back as the API endpoints, which is the top ranking results. So it's still processing. I see that it's loading. The top 10 is loading. Okay, you can see. So after I put the picture there, you can see that it's a black running shoe, and it gives us as the first result, gives us black running shoe, and then it brings other results that are related to the black running shoe. You can see grey athletic shoe and all of that. So all of this, so you can use both text. You can put the text black running shoe. You can see black running shoe, and also you can see it has changed to multimodal search, and then you can search both of them and to give you a accurate result. So you can check out this project in my GitHub, and you can also run it and test it for yourself. Thank you.